that is in fact what they've done through plant breeding, is to improve this part of the equation. But I don't think their paper actually has data that are consistent only with that hypothesis. So let's move on to the other part of the equation. The water loss from the leaf is proportional to the water vapor concentration right inside the stomata minus the water vapor concentration right outside the stomata. That's what drives water loss through the stomata. And here, there's perhaps some potential for improving both of these. These are really, they're not directly under physiological control at all. The water vapor concentration in the leaf interior surfaces have to be wet or the leaf is dead, and a wet leaf surface at a given temperature is going to equilibrate with a given water vapor concentration. So it seems like, this physics that you can't get around, but that assumes there's nothing that we can do about the temperature term. And then, if we could have lower temperature, then we have lower values of this and therefore less water loss. And similarly, the water vapor concentration in the atmosphere seems like something that's beyond our control, it's just out there. But this is something that varies over the course of the day as well as over seasons of the year, as does leaf temperature. So if we alter the time of year when we're growing a crop, or we alter the time of day when most photosynthesis and transpiration are occurring, either one of those can affect water use efficiency. And I actually have an example in my book. The citation that I give, I'm not sure is linked to this story that I'm going to tell you, so I'll tell you the story. My friend Steve Spaeth worked for USDA in Pullman, Washington a number of years ago, and he had a student that came to him and said, I'm from this country where drought is a real problem for production of this crop, and so what I want to do is use genetic engineering to improve water use efficiency. And that may be a goal that we're getting closer to today, but this was quite a few years ago when, it was long before, high throughput sequencing and so on. And so Steve said, well, yeah, I understand that genetic engineering is the wave of the future, but it's not the future yet. Tell me more about, your country and what's going on. Well, we grow this crop during the hot, some hot, dry summer season, and we run out of water. We have this wet season, but we can't grow the crop then because there's this disease that would wipe out the crop. And so Steve says, well, water use efficiency would be much higher in the winter when, or the wet season when things are cooler and wetter. And plant breeders have this fantastic track record of breeding for disease resistance. So why don't you breed for disease resistance, grow your crop in the high humidity season, and that's going to give you your higher water use efficiency. And so I understand that they actually did that, and I have a citation in the book for somebody who did that. I'm not sure whether that's the same country and the same person or not. But so that's a seasonal difference in humidity. But there's also this difference in humidity and in leaf temperature over the course of the day, such that the water use efficiency, that is the ratio of photosynthesis to transpiration, is higher in the morning. It's really high at sunrise, but of course your photosynthesis isn't all that great at sunrise. But this period here, you can get substantial photosynthesis and do that while using substantially less water per unit of photosynthesis than later in the afternoon. This seems so simple. And surely there must have been mutations over the evolutionary history of the wild ancestors of our crops. Surely there must have been mutants that arose that closed their stomata, at least partially during the afternoon, left the stomata open in the morning, thereby got higher water use efficiency. Why didn't this wonderful genotype take over and be inherited by the wild ancestors, or be inherited by rice and wheat and so on today? Well, because these altruistic plants that closed their stomata in the afternoon, thereby leaving more water in the soil so it could be used later, so it would last for more weeks and not run out, they left the water in the soil, and the cheaters who hadn't evolved that trait took that water, and even though they were using that water less efficiently, they grew taller and produced more seeds than the more efficient genotype that was using water more conservatively. So this is the case where, all else being equal, natural selection will favor water use efficiency. But if all else isn't equal, if to get higher water use efficiency, you have to leave resources in the soil to then be used by a competitor, natural selection is going to say, well, forget efficiency, I'm going to grab more water. And so that's my hypothesis for what's, I'm suggesting that there may, in fact, this may be the basis of the higher water use efficiency of dry-scale wheat, that is, opening its stomata primarily in the morning, closing them at least partially in the afternoon, and that's certainly something that can be tested. And the other thing that will be interesting to test is get the parental material and do this kind of competition experiment like I showed earlier with the barley and the wheat. And they don't look differently, but we can identify them through PCR or something like that. See whether this high water use efficiency wheat put in competition with its parent, whether it would win or lose in competition over a range of environments. Now let me turn to my third and last example of possible opportunities for improvements that would have been missed by natural selection. This is most directly relevant to soybean, which are not growing yet, but certainly rice has various endophytes that it can be infected by that may be more or less beneficial, and it also has root-associated microbes that may be more or less beneficial. And the rice itself may have effects on various soil properties that would affect a subsequent crop. And the method that I'm going to propose would actually work for any of these. It's not really symbiont specific, but I'll use the symbiont example to illustrate the point. I've already shown this graph, so I'll skip over it, showing the effects of corn enriching the soil with endophytes that are beneficial to soybeans. But this is what I've spent most of my career working on, the legume rhizobium symbiosis. And this graph, each of these data points is a different genotype of rhizobia. They're all inoculating the same plant genotype. The vertical axis is the benefit of the rhizobia to the plant, and that's measured by yield increase with inoculation. The horizontal axis is sort of the benefit of the plant to the rhizobia. Strictly speaking, it's nodule mass per plant, but all else being equal, a plant with a larger nodule is contain more rhizobia, and so those rhizobia, when they go out in the soil, they'll outnumber the rhizobia from a smaller nodule. So nodular mass is at least sort of a measure both of the benefit of symbiosis to rhizobia and also of the cost to the plant of that symbiosis. So we can group these rhizobial genotypes into 3 general categories. This group here, I would call losers. They're strains that are not good at nodulating or not good at occupying nodules, and so they don't provide any benefit to the plant simply because they don't occupy many nodules, but they're not taking much benefit themselves. And the important thing is they're not occupying nodules that could otherwise have been occupied by these more beneficial strains. So, you know, these guys aren't falling below 0 in terms of effect on yield, but I would still call them harmful because they're, to the extent that they do occupy nodules, they occupy nodules that could have been occupied by a better strain. But the rhizobia that I'm really worried about are these cheaters. How are these cheaters? They're providing as much benefit as the strains that I call cooperative strains, but they're doing that at least some of them are, but they're doing that at a higher cost to the plant. So you'd really rather have something that had a benefit at a lower cost, and some of them, I mean this one in particular, you can see that it's providing less benefit than this one up here is the most used inoculant strain for soybean. So this strain is the worst of the cheaters at providing less benefit, and yet it has a higher cost than any of these beneficial strains. So I've argued that we could substantially increase the benefits to soybeans from rhizobia if we could increase the fraction of nodules that are occupied by the most beneficial strains. And so one question, of course, is, well, what's the deal? Why are soybeans stupid enough to let these guys into their nodules? And I think it's kind of like the airport security question. You know, do you really want to keep people with certain names, like, you know, Kennedy, off of airplanes, or do you want to keep people with knives off airplanes? The initial stage of letting rhizobia into a plant is like the stage at airport security, where they ask you to show your identification and they, you know, see if you're on a list of prohibited names. But like the metal detectors or X-ray machines at airports, soybeans have a second line of defense that doesn't care what signal molecules the rhizobia has, but judges them based on their actual performance. And I think the first evidence for this actually comes from John Sheehy and colleagues many years ago, when they called it the acetylene-induced decline or the argon-induced decline. But what we've done in this experiment is to inoculate a plant with a nitrogen-fixing strain of rhizobia and then enclose nodules in these individual chambers that allow us to control the gas atmosphere around the nodule. One of the nodules has normal air with 80% nitrogen and 20% oxygen, so normal nitrogen fixation in that nodule. And then in this nearby nodule, we substitute argon for the nitrogen, and so we have a rhizobium strain that has all the same signal molecules as a nitrogen-fixing strain, but is unable to fix nitrogen in this chamber because there's no nitrogen there to fix. And the plant responds to that with what we call host sanctions, and we measure that as the number of rhizobia per nodule. More recently, we're also measuring the resources per rhizobium cell that they're taking from the plant, but this is older work. And you can see that on a per nodule basis, you know, each of these nodules is founded by a single founderous rhizobium cell. There's 2 or 3 times as much rhizobium reproduction inside the nodule if they fix nitrogen than the same strain if it doesn't fixed nitrogen. Well, an evolutionary biologist will tell you that a 5% difference in fitness is huge in terms of, just a few generations it goes to fixation. Here we've got apparently a 2- or 3-fold difference in fitness. Fitness loss if the rhizobia tried to cheat their host by not fixing nitrogen. So much of this difference is due to differences in nodule growth, although there's also a small difference and that's actually something that was observed many years ago. Somebody showed that nodules with non-fixing rhizobia don't grow as big, but because they were agronomists only thinking about yield, they didn't bother to count the rhizobia per nodule, and therefore I got the paper in Nature, and they didn't. They were in agronomic journals somewhere. But anyway, moving on to the opportunity for improvement, Toby Kears, who did this work, repeated this experiment with not just nitrogen-free atmosphere, but a low nitrogen atmosphere, different amounts of nitrogen to get a whole range of nitrogen fixation potential from 100% of the potential fixation by this strain down to 0%. And if we compare the rhizobium fitness, this is a log scale, and actually these 3 lower rates of nitrogen fixation, all of them were statistically significantly lower rhizobium fitness relative to full nitrogen fixation. But these rhizobia were fixing nitrogen at only 50% of capacity, and yet the difference in their fitness wasn't statistically significant. It's sort of a hit or miss whether they were going to get hit with strong enough sanctions to reduce their fitness. So this, I think, may explain what I showed several slides ago, that there are cheaters out there. There are actually in Midwest soils, there's a lot of serotype 123 that's really good at nodulating soybeans, and it fixes a little bit of nitrogen, but not nearly as much nitrogen as the inoculant strains. And so my guess is that's sort of a moderate cheater that doesn't cheat enough to trigger sanctions. Has natural selection been asleep at the switch? I mean, these cheaters must have been out there for the last 50 million years or so, and certainly post-sanctions have evolved, but why are they so weak? Why don't soybeans and other legumes, I haven't actually looked at wild soybeans, but if the ancestors of soybeans didn't impose sanctions on 50% cheaters, why not? Now, wouldn't it be better to get rid of those things and not have them in the soil next year? Well, that's next year. That's somebody else's problem. I've got seeds to make. They need nitrogen. These nodules, they're not fixing as much nitrogen as I would like, but they're fixing some nitrogen. I'm not going to shut them down. I'm thinking about my individual cost benefit, not the benefit to future generations of soybean plants. Is this theme starting to sound familiar? I hope so. But we can make a different choice. We can say, we're willing to give up 2% yield this year to enrich the soil with the best local rhizobium strains so that we get 50% higher yield next year, and the year after that, and the year after that. I just made up those numbers to make it sound like a wonderful idea. It might not be that big of an improvement. Well, if we want to do that, we would need either of 2 approaches. Either we would need to figure out what's the mechanism of sanctions, and then go in and do some kind of genetic engineering. And actually, a lot of really smart people, well, I didn't show the data, but it looks like the mechanism, the physiological mechanism of sanctions, is that this failure to fix nitrogen triggers a decrease in the gas permeability of the nodule, and that limits the oxygen supply to the nodule interior and reduces the respiration of the rhizobia inside. The legume nodules have this variable diffusion barrier that functions kind of like stomata. That's work that John Sheehy was one of the first to really demonstrate that. And a lot of really smart people have worked trying to figure out, okay, so the permeability decreases, but what exactly is going on? You know, is it ion channels? Is it some sticky stuff that's secreted into the intercellular spaces? What's going on? And I think everyone has at least temporarily given up on that problem. So, you know, if I had a big grant, I'd work on it, but I don't. But we could just take a more traditional breeding approach and say, okay, well, it'd be nice to know the mechanism and genetically engineer it, but is there any genetic variability in this trait? And so we think so. This field experiment isn't really a perfect test of the question of whether there's variability for host sanctions. But what Toby did was to grow a bunch of cultivars of soybean released from 1937 through 2001, and she grew them in a soil without indigenous rhizobia, grew them both with highly effective rhizobia and with a mixture of good and bad rhizobia. And then in the upper graph, she's calculated how well the soybeans yielded in the mixture of good and bad rhizobia relative to if they were with good rhizobia alone. And so there are various ways that you might explain this result, but certainly one explanation would be if you had really good sanctions, then the rhizobia, the soybeans that had a mixture of bad and good rhizobia would shut down all the bad rhizobia nodules, put all the resources into the good rhizobia nodules, and they would then have pretty much as good yield as they would get with only good rhizobia. Whereas cultivars that had weaker sanctions wouldn't do that. They would continue to support these bad nodules and have lower yield. And so what she found is that these three older cultivars all did fine with a mixture of good and bad rhizobia, but the new cultivars didn't. Now, if you look at the yield of these new versus old cultivars, either with nitrogen fertilizer, blasphemy, but you know, it's an experiment, or with only good rhizobia, of course there's been all this yield advance, and the new cultivars have much higher yield. But this effect, this inability to deal with bad rhizobia is so severe that growing them with this mixed inoculum, it essentially eliminates the yield benefit or the yield gain of the modern cultivars. So these results are consistent with these older cultivars having retained stronger sanctions and those sanctions having been lost through decades of breeding in high nitrogen soils. That's not the only possible explanation, but it's certainly a possible explanation. So maybe there's genetic variability for this trait, whether or not that's what this shows. But we need some kind of selection scheme, and the selection scheme that I'm proposing was motivated by this particular example of developing soybeans that would impose really strict sanctions on bad rhizobia so that they would, at the end of the growing season, they would release billions of good rhizobia from their nodules, and the bad rhizobia would all die or be released in very low numbers, so that growing these soybeans, rather than inoculating this wonderful strain of rhizobia, which then disappears, which is what typically happens, you grow a legume that selectively enriches from the pool of locally adapted rhizobia, selectively enriches the soil with only the best strains. Now obviously, this same argument could go for something that would selectively enrich the soil with only the best mycorrhizae, or selectively enrich the soil with only the best pseudomonads that are doing disease control by using antifungals on the root surface. Or this selection scheme would also work for direct plant effects if a plant somehow did something to the soil that was beneficial to the next crop in the rotation. So this is kind of a cartoon. I don't know if you do it exactly this way, but let me just explain the logic. So start out with a genetically diverse soybean population. I should have drawn them, different sizes and colors to make the point that they're genetically diverse, but they're genetically diverse, and they're growing in either pots or some, nicely defined, GPS location in the field, so we know exactly, what soil they're in, and they're growing in some real-world soil that has a mixture of more and less beneficial microbes. So we grow them to maturity, harvest the seed, measure the yield, but we don't decide which seed to advance based solely on the yield of this crop. Instead, we come back with the next crop in the rotation. And in this case, we're using a genetically uniform test crop. All these corn plants are the same genotype, but they grow differently because of the effects of the previous soybean crop. And so based on that, we say soybean genotype 2 and 4 look like maybe they have enriched the soil with mycorrhizae that are beneficial to corn. Let's keep 2 and 4 and discard the rest. And then we go in with the next crop in rotation. In this case would be soybean. And again, here we're using genetically uniform test crop, and we see that soybean genotype 2 has some lasting effect on the soil that benefits soybean. So that's the one that we would pick from this set of 6. I think I'm about done, which is good time. So to summarize, crowding responses that maximize individual fitness aren't necessarily those that are, certainly not those that are best for yield potential, but they may also not be best for weed suppression. There may be some opportunities there. I proposed looking at more uniform spacing, but I'm not a rice expert, so I don't know if that's practical or not. I suggested that when we think about water use efficiency, we should be thinking about not just the individual plant perspective, but the whole plant community and what kind of traits would perhaps be more efficient in terms of a whole field of plants. And finally, something that natural selection hasn't done. It doesn't have any view to the future, but we do think about how this year's crop genotypes might affect the growth of subsequent crops. It's 10 o'clock, some of you may have to leave, but I'll be happy to take questions for any of you that